You're welcome to this channel, and if this is the first time of coming across this channel, kindly subscribe to this channel and click on the notification icon to get notified when we release new video. What are we learning in this video? This video is a continuation of wave. We are talking about stationary waves, so we are going to solve question. In the previous video, we have learned all the theories behind vibration of string and vibration of air in color. Now we want to solve some example. If you haven't watched the previous video, kindly watch the previous video, as the previous video will guide us on how to solve this question. All right, without further ado, let's start solving the question. Now let's start applying what we have learned so far to solve question. The first question is the wavelength of the first overtone of a note in a closed pipe of length 33 centimeter is. Now looking at this question, what are we asked to find? Wavelength. Okay, wavelength of the first overtone when the length is 33 centimeter. Now it's very simple, very simple. Since you are asked the wavelength, what you just need to do is the diagram. The diagram, if you don't want to cram anything, I don't encourage cramming. The diagram. Now look at first overtone. First overtone means what? Second harmonics. So let's see how to solve it very fast. So we have the solution. Now, for second harmonic, we are going to have something like this. In closed pipe, you have something that looks like this, just like this. And then you have something like this. This is the diagram. This is your L. L is here. Now, looking at this, if you count it 1, 2, 3, it means that what? 3 lambda over 4 is equals to L. So we have, what will now be lambda? Lambda is equals to what? 4L over 3. Just substitute the value. What were you given in the question? You are given the length, 33 centimeters. So you have 33 times 4. Let me come again. So you have 33 times 4 over, what is this? Over 3. So you have 3 here. 3 in 33, you have 11 times 4. So you have 44 centimeter. Now you need to convert your centimeter to meter in SI unit. Okay, centimeter is what? Is 0.01. So you now have 44 times 0.01, which is equals to 0.44 meter. You might choose to solve it using another way by converting the length to SI unit before you plug it in inside your formula, and then you get 0.44 meter. That's how to solve this question very fast. Going back to the question, we are asked first overtone, right? Overtone, first overtone means what? Second harmonic. Second harmonic for closed pipe. Second harmonic for closed pipe. So what are you given in the question? You are given the length, which is what? The length of the closed pipe, which is 33 centimeters. So let me quickly write what I've applied here, the method of solving this question. This is what I know. I know that second harmonics is equals to what? First overtone. That is what I use to solve this question very fast. Then I have this diagram. Now let's solve the second question, which is find the frequencies of the first 3 harmonics of a piano string of length 1.5 meter if the velocity of the wave on the string is 120 meter. How do we solve this question very fast? Let's understand this question. We're asked to find the first 3 harmonics of a piano strings that you are given the length, which is 1.5 meter, and you are given the velocity of the wave that is produced, which is 120 meter. Now, what you just need to do is you can easily find the first harmonic frequency. You are given the length, and the length is having relationship with the wavelength. So you can find the wavelength, then you can find the frequency, the first harmonic frequency, and use the knowledge of vibration of string, the relationship between the first harmonic, second harmonic, third harmonic. So we all know that for the vibration of string, it has even and odd harmonics. F1 ratio, F2 ratio, F3 is equals to 1 ratio 2 ratio 3 and you continue like that. Now we are given some parameters. So given that, the first thing that you're given is L, the length of the string, which is 1.5 meter, is already in SI unit. Okay, then you're given velocity V, which is equal to 120 meter per seconds. So this is what you're given in the question. Now for the first harmonic, you have something that looks like this. First harmonic for vibration of string, you have something that looks like this and like this. So you have L is equals to what? Lambda over 2. So we know that L is equals to lambda over 2. So lambda is equals to 2L. Okay, so yeah, let's find the wavelength, which is the lambda. So which implies that lambda is equals to 2 times 1.5 meter, and that will give you 3 meter. This is the wavelength. Okay, is there a relationship between frequency, wavelength, and speed? You know that V is equals to what? F lambda. So velocity is equals to frequency multiplied by the wavelength. So you have, just substitute the value. Okay, just make frequency solve the formula. Making frequency solve the formula, frequency you now be equals to what? V over lambda. So yeah, put the value. What is your V? 120 divided by, what is lambda? 3, and that is 40 hertz. What frequency do you find now? This is the fundamental frequency, F1. And you know that for vibration of string, F1 ratio F2 ratio F3 is equals to what? 1 ratio 2 ratio 3. So therefore, F2 is equals to what? 2F1. So 2 multiplied by 40 hertz, and that is 80 hertz. Okay, what is F3? F3 is equals to what? 3 F1, which is equals to 3 times 40 hertz. So we have what? 120 hertz. Okay, now the frequency that we find, F1, is equals to what? 40 hertz. F2 is equals to what? 80 hertz. And F3 is equals to what? 120 hertz. Let's just have it here. Simple as that. Let's see how to solve this beautiful question, which is a closed organ pipe and an open organ pipe emit notes of the same pitch. The ratio of the length of the air column in the closed pipe to that of the air of the open pipe is. Since the notes are of the same pitch here, it means that they have the same frequency. So let's understand this question very well. Notes of the same pitch, notes of the same frequency. So we want to find the ratio of the air in closed pipe to that of open pipe. We are talking about vibration of air in closed pipe and open pipe. Now, since the velocity of the wave generated will also be the same here, it will be the same, frequency same, and recall that the length of air in each column will be corresponding to the wavelength. It has a relationship with the wavelength. So we can use that knowledge and solve this question very fast. Now let's just see how to solve this very fast. Now let's have L close. Now you will pick just the fundamental frequency for the two of them. Just assume we are talking about fundamental frequency here. You can pick the first harmonic or second harmonic or third harmonic, and you still get the same answer. But I will advise you to pick the first harmonic. Okay. Now for the first harmonic frequency for closed pipe, you remember that LC is equals to what? Lambda over 4. If you have forgotten, this is close. You have a pattern like this. This one is L, isn't it? So L is equals to what? Lambda over 4. Okay, so lambda here will be equals to what? 4LC for this guy. Now let's come over to open pipe. Now for open pipe, L open will be equals to what? Lambda over 2. So if you have forgotten, you have something like this. You have something that looks like this. This is your, sorry about that, just manage it. This is your L here. Now, L is equal to what? Lambda over 2. How is it lambda over 2? You have 1, 2, 2 out of 4. Okay, so lambda here will be equal to what? 2L open. 2L open. Okay, so that is lambda for this guy. Okay, now this is what we are going to do very fast. Very fast. F is the same for them. So let's try to make lambda sort of formula in V is equals to F lambda. So lambda will be equals to V over F. So V over F. Now what is lambda for this guy? So we have 2, so we have 4, sorry about that, 4 LC is equals to V over F without wasting time. So we now have LC is equals to what? V over 4F. Just try to divide both sides by 4 for this guy. Come over here as well. For this guy, so you have, this one is L open. So you are going to have what? 2L open, which is lambda, is equals to what? V over F. Now you have L open is equals to V over 2F. All right. Now, L close ratio L open will give you what? V over 4F ratio V over 2F. Okay. Now, between 4 and 2, which one is the greatest? 4 is the greatest, so you can multiply all through by this. We have been doing this. LC ratio L open will now be what? V over 4F times 4F over V ratio V over 2F times 4F over V. So V, we cancel V here. Okay, 4F, we cancel 4F here. You are left with 1. So let's have it here. LC ratio L open. The first one, we have reduced it to 1. Come over here. V, we cancel V here. F, we cancel F here. 2 here. 2. So ratio 2. Can we solve this without going through all this stress? Yes, we can solve it. Now, what can we use to solve it? Understanding of mathematics very fast. Ratio, rate, and proportion variation. That is what we can use to solve this question without wasting time. Let me give you a clue on how to solve it. So just come over here to the closed pipe. Now look at the formula. L is equals to lambda over 4, which shows that the wavelength will be divided by 4 to get the length. Okay, now it is dividing by a factor of 4. Okay, now come over to the open pipe. The wavelength is being divided by 2. Okay, by factor of 2. So you now have what? 2 and 4. But don't forget that they are acting as a fraction. 1 over 4 and 1 over 2. Between 1 over 4 and 1 over 2, which one is the greatest? 1 over 2. So that is how you can solve it without passing all through the stress. So you divide lambda over 4 times 4 over lambda ratio lambda over 2 times 4 over lambda. So you get 1:2. Now let's solve this next question, which is if the fundamental frequency of a closed pipe organ on a day when the speed of sound is 640 is 160 Hz, then the length of the pipe is, this one is very simple. If the fundamental frequency, so let's have our solution. This one is very straightforward. In the question, you are given V, isn't it? V is equals to 640 meter per second, and then you are given F, which equals to 160 hertz. Now, looking at this question, you are asked to find what? To find the length of the fundamental frequency. Don't forget, we are talking about fundamental frequency here. So you have F1 here. Now, you need to find the wavelength. Once you get the wavelength, you can get the length of the close pipe. Okay, so we don't know the wavelength, and we don't know what? L is unknown. So yeah, let's quickly find the wavelength. Finding the wavelength, phi is equals to what? F lambda. So lambda will now be what? V over F. What is the value of the V? 640 divided by 160, 0, 0. So you have 4. This one is what? 4 meter. Now, what are we talking about here? Fundamental frequency of a closed pipe organ. Let me quickly show you the diagram. Please watch the previous video. This is closed pipe. It looks like this. Fundamental frequency looks like this, something like this. Just manage it. So we have L, close. Oh yeah, what is the relationship? Is equals to what? Lambda over 4. Okay, so we have LC is equals to what? Lambda over 4. So which is what? 4 divided by 4. And that is 1 meter. Very fast, simple. The next question, two turning fork of frequency 256 Hz and 260 Hz are sounded close to each other. What is the frequency of the beat produced? This one is very straightforward and simple. So if you want to find the frequency of beats when two things are being sounded together, what you just need to do is you find the difference between them. You find the what? The difference. So the beats will now be equals to what? Very fast. 260 Hz minus 256 Hz. So you are going to get what? 460 minus 56, so you have 4 Hz. As simple as that. So the sixth and the last question, which is if the tension is maintained on a stretched string of length 0.6 meter such that its fundamental frequency of 20 Hz is excited, determine the velocity of the transverse wave in the string. How are we going to solve this? Now look at this question very well. You are given the length of the string, okay? Then you are given the frequency, fundamental frequency. They ask you to calculate the velocity. All right, this is vibration of string. This question is straightforward. What you just need to do is find the wavelength, which is the lambda. You are given the length of the string, so you can use it to find the wavelength because we are talking about fundamental frequency. So given that L is equals to 0.6 meter, then you are given the frequency, fundamental frequency, which is 220 Hz. Okay, then know the wavelength. Wavelength is unknown, and you are asked to find the velocity. You didn't know the velocity as well. For the fundamental frequency of vibration of string, we all know that L is equals to lambda over 2. So when we find the value of lambda, lambda will be what? 2L. Now substitute the value. You have 2 multiplied by 0.6 meter, and that is 1.2 meter. Okay. Now using the relationship, which is using V is equals to F lambda. So what will now be V? V is equals to the frequency in the question, which is 220 multiplied by the wavelength that we've calculated, 1.2, and that's equals to what? 220 times 1.2, that would be 220 plus 44, and that will give us 264 meter per second. Now, how did I get 264 very fast without using a calculator? Using mathematics knowledge, just like expansion. So we can have 220 open bracket. 1.2 is still the same thing as 1 plus 0.2. So I close bracket. 220 times 1, that's 220. 220 times 0.2 is still the same thing as 22 times 2, that is 44. Okay, 22 times 2, and you are going to get 44. Now you now have 220 plus 44, which equals to 264. Alright, that is all for now. Make sure you watch the next video. Were you able to learn in this video? Please comment if this video is helpful. Like, share this video, subscribe to this channel, comment what you're able to learn in this video. In the next video, we are going to learn sonometer, which is also known as monochord. Please make sure you watch the next video, and we're going to be solving question. All right, thank you for watching this video. Subscribe to this channel. Bye for now.